All right, so for this final exam, I plan to release it this Sunday at 7:00 p.m. and it will be due Monday at 7:00 p.m. That way you have 24 hours to complete it. I will be available on Zoom Monday morning and afternoon for questions and answers to kind of clarify things in terms of the exam. Hopefully it's not too much. You should expect 5 to 6 questions on this exam that can have multiple parts, similar to what you've seen on the homework and the midterms. I will post today a final exam review to kind of better equip you and manage the expectations on what I'm hoping you've gotten out of this course in terms of your knowledge and skill set in membrane science and engineering. But this lecture today is to kind of help reemphasize those key things I want to point out, as well as to provide another mechanism for you guys to ask me questions and we can discuss any of the issues you may have going into the final. So we've covered, I would say, quite a bit in this class, but in terms of looking at, okay, what are the specific things in the textbook do I really need to look at and refamiliarize myself with? So I'd say we'd really hammered in the first 10 chapters of Baker's book. And so when we're looking at that, we looked at an overview of membrane science, the kind of terms associated with membranes, and this thing likes to jump around. And we talked a lot about transport in/through membranes, I don't know why that word disappeared, but it did. And of course, we looked at polar flow models, solution diffusion, model, and then the kind of the in-betweens briefly, but I probably, if I'm honest, won't emphasize them. But definitely be familiar with the pore flow driven model and the solution diffusion model. Right? If anything, you'll know what solution diffusion means from after taking this class. Then we looked at membrane modules and the pros and cons of each of those. We looked at, isotropic versus anisotropic membranes. We talked about, this interfacial polymerization. We talked about phase inversion. We had the baths and things. Then we looked at the modules themselves, looking at flat sheet, flat plate systems. We also looked at spiral round modules. We looked a little bit about the tubular membranes. And then the more important, bigger thing was the hollow fiber. Right, so I would say that the key ones being these three. Tubular is less pervasive in membranes, but definitely spiral round hollow fiber for a lot of applications. Flat plate is useful, especially for experimentation and doing lab work in terms of looking at performance. We talked on concentration polarization. And looked at a boundary layer model for concentration polarization. And we looked at the film model. Right, and so, how Peclet influenced that. We talked a little bit about, cross flow versus co-current versus countercurrent. And how this applies to both liquid and gas-based separations. All right, so let me go ahead and stop here. Are there any questions, or is there anything in particular that you'd like me to kind of dive into in greater detail or reemphasize? Is there anything I can kind of further clarify on, or you want to talk about a little bit more?
So I have a question on gas separations.
Okay.
So basically, with the gas separations, when you have the what do you call the what's that ratio of the feed and the permeate? What's that called again?
You talk about the pressure ratio?
No, not the pressure ratio.
Or the stage cut?
Yeah, stage cut. So how do you? So in the PowerPoint that you gave us, you said that when you increase the stage cut, you also increase the effective membrane area. How do you actually find that amount of area?
You don't technically increase the effective membrane area, but the necessary area to do the separation you want will go up. Does that make sense?
Yeah, is there a way
You can still increase this. Well,
okay.
You really can actually. It just means the necessary area that to obtain that stage cut will be increased, right? Because the if I put a certain feed in at a certain pressure ratio, I'm going to get a makeup of the retentate and the permeate. I can't do anything in terms of that cut without changing either the pressure ratio or the amount of membrane, right, in the system.
Yeah.
And so that's what it's really getting at.
Like, is there any way to actually calculate that, or is it just a generic relationship?
You can calculate it based off of the transport models in terms of the required, depending on the system, you can determine the expected flux through the membrane, and then based on your desired flow, you can figure out what the membrane area needs to be. And we've done that in several of the homeworks in some of the midterm exam problems.
Okay.
But outside of that, that's all you can really do. That was just that figure was just trying to really reemphasize that, the higher the stage cut, the more area you're going to need to get that, to achieve that stage cut for a fixed pressure ratio.
Okay.
You also have to keep in mind is even if your pressure ratio gets so high, you're still going to be selectivity limited, which means that you're not going to be able to achieve, an even greater stage cut beyond that. Does that answer your question?
Yeah, that makes sense. Thank you.
Of course. Any other questions, things that kind of gearing towards these introductory sections, looking at transport, the modules, and concentration polarization, things that you want me to clarify, things that you're still kind of fuzzy about?
For me, it's to get the the stage cut. I don't really know what that is, other than like I know what the textbook says, but I still don't really get it. It's like a
Okay.
percentage of the permit
So
to feed.
to clarify, you're still a little confused on stage cut,
Yes, sir.
correct? Okay, so stage cut is an operational parameter that denotes, for a given system, right, where I have my feed, my retentate, and my permeate. I can make that better, right? So this tells me what's the ratio of my permeate flow rate over my feed flow rate. So it comes from, if you have a membrane process with multiple stages, you're wanting to look at how much flow is being cut at each stage. Primarily, because especially when it comes to gases, when you're looking at efficient operation, you want about the same cut through each stage, because in terms of compressor duties and overall process operation, it's a lot easier to handle, and it actually comes out for more efficient than anything else. So that's really where the term comes from. But it's, if I have 100 standard cubic feet per minute coming in, and my retentate's 70 standard cubic feet per minute, my permeate's 30 standard cubic feet per minute, then my stage cut is 0.3, right? Because 30% of that feed is going to the permeate. And it influences some of the assumptions we make, primarily when it comes to the driving force of our process. If we have a low stage cut, which is typically probably less than, I would say 0.1, 10% or less, we can assume that driving force CI naught and CI in the retentate are about the same. And so the overall driving force can be, I'll write it down, can be our feed over our permeate, or probably a little more accurate as the retentate. Right, and so this gives us that like CSTR assumption. But at high stage cuts, CI naught is not equal to CI retentate. And so the driving force becomes, feed over permeate, at minus or average the retentate over the permeate, right? So we get that log mean driving force. In the plug flow reactor assumption. And so theta is a good way to measure that.
So can I ask a question?
Of course.
So how does the module change the stage cut?
What do you mean?
Like, I don't understand what you mean by calculating the stage cut for each module. Isn't the mass balance firm?
Well, yeah, the mass balance is going to tell you what the stage cut is. But if you have a multi-module system, you're going to have to break that up. Does that make sense?
Yeah.
Your mass balance is going to look different if you have a single stage versus a two stage, three stage. Are you going to have recycle? What is the recycle going to look like? And so all that's going to influence your quote unquote stage cut.
So
Right.
if we're just assuming a one stage, so.
Well, if you're assuming a one stage, then your stage cut is as you've shown here, right? But I can come up and look at a different system. Now, you know, if I have something that looks like this, where this is feed, this is retentate, this is permeate, right? And then I do this through use of a recycle. Now my stage cut looks different, right? Now my theta is going to be my feed and my recycle, excuse me, my permeate over my feed and my recycle. And what this allows me to do is tweak theta as an operational parameter. Right? It doesn't give you a big window, but it gives you a window in terms of how you can now I can make this a process parameter instead of a fixed by the conditions of the membrane and the module itself. Right? Now in this case, I can lower the stage cut as I want. If it becomes advantageous. Any other questions? These are all good questions. I appreciate them. No? Okay. So let's keep moving on a little bit. And then I'll pause one more time. So we looked at chapter 5, reverse osmosis, looked at how do we calculate osmotic pressure, delta pi, right, which is what Z delta C RT. And we talked about, I'm trying to think what else, our A and B parameters, permeability coefficients. And when we looked at water flux, which is A delta P minus delta pi, and for our salt coefficient, which was B delta C, or I should say C J naught minus C J L. And of course, we had rejection. And we had the other expression, which I would probably need to jump to the book because that one I don't remember off the top of my head. Which was a function of our permeability coefficients. 1 minus rho sub I, B over A delta P minus delta pi times 100. And then we looked at a little turn, a bit of RO operational parameters. A little bit of fouling and things like that. Any questions on reverse osmosis and what you might see on the final, or things that I can clarify?
Excuse me, could you clarify the driving force for reverse osmosis more detail?
Yeah, I
Because
get that. It's a little tricky.
yeah, because yeah.
Yeah. So the driving force for the reverse osmosis is going to be your feet, your pressure difference. Which is your delta P minus delta pi, or and you know it's going to be your P naught minus PL minus your osmotic driving force resisting the force. You know, sometimes we can look at this being the key driving force, and then the total can be the net driving force. But you know, you can argue that they're both kind of the driving force. Correcting for the osmotic pressure is going to be more accurate, though. I'll try to be more specific on the final if I put one of these problems in. How's that?
Oh,
Because in the exam, like in the exam we did the second midterm, you said that what's the effective driving force? And I like wrote delta P minus delta pi, and you said it's incorrect.
Did you say delta P minus delta pi, or did you actually give me the numbers?
I said delta P minus delta pi and gave you the numbers.
Like, you can send it to me and I'll take a look.
Okay.
Or you, yeah, just send me an email and I'll look at it one more time. Any other questions?
Is there like always like, is it dependent on the case, or is it like depending on like which kind of membrane you're looking at or separation process whenever you're looking at what the driving force is? Does that make sense?
It's mainly the process, not necessarily the membranes themselves.
Okay, so like for that, it's always, from my understanding, we've always been using pressure, but what cases is it concentration or something else?
I think we had looked at a couple different situations where it wasn't necessarily pressure. It really depends. See, that's tricky because, you know, if we really want to go back to it, yeah, I don't want to get too lost in the weeds here. Pressure is the easiest for a majority of separations, primarily because that's what's being used as a driving force, if that makes sense. A lot of systems rely on the application of pressure to drive flux through a membrane. Anything outside of that is going to be looking at, like, for example, if it's concentration driven, a lot of that's going to be a diffusion mechanism. When we looked at, you know, some of the, in brief, looking at that Knudsen diffusion and things like that, that's concentration is going to be a bigger factor in those circumstances. But we use pressure primarily because that's typically what's being applied to enact the separation, right? And keeping in mind the key driving force is, you know, what's the easiest approximation for our chemical potential difference, which is what's driving the separation to begin with. And so that's why in most of these processes, pressure is used, because we can easily control it, we can easily monitor it, and we can relate it to what we get in terms of performance through these membranes. Some of the more biological processes are going to rely on concentration more, primarily because they're going to be diffusion controlled. You know, things like the dialysis system is going to be diffusion controlled more than anything. The ion exchange membrane processes, which we touched base on, isn't going to be pressure driven, it's going to be current driven, because we're using that as our driving force instead. And some of the more we didn't get to facilitated transport in biosystems, primarily because We just kind of ran out of time, so I apologize for not getting into more of that. But a lot of those systems are going to be more concentration and diffusion dependent than the more traditional liquid and gas space separations. Primarily because especially when you're looking at biological systems, you can't rely on pressure because the body really can't handle too much. And so a lot of those are going to be looking at diffusion coefficients and concentration more so than anything to describe the quote unquote driving forces that enact the separation. Any other questions? All right, so keep trucking. We touched on ultrafiltration. And in this system, we looked at ultrafiltration, a little bit of characterization. And we looked at, let me jump to it, make sure I don't skip anything. We looked at the influence of fouling. We looked at gel layers, calculations. We had our, bringing in some of that Peclet stuff back in. Looked at critical flux. Right, and so other things you want to keep in mind, molecular weight cutoff. Now we determine those. Those make good problems. And then we mainly looked at batch operations. And we talked a little bit about feed and bleed systems, which are really just multiple pass operations. All right, and a lot of times we're going to rely on some form of recirculation to make sure that those flow velocities are high to keep those fouling layers in check.
Excuse me?
Yes, you have a question?
Yeah. For this one, could you send us the solution for homework 6 because it's related to this one?
Yeah, I'm going to upload all the solutions to the homeworks on
okay,
Blackboard by the end of the day. I'll send you an email when I do.
Okay, that's good.
Yeah, for sure.
Yeah.
So that's the big things we took out of ultrafiltration. For microfiltration, we looked at pore characterization. Right, calculating the bubble points. Delta P is 2 gamma over R, cosine theta. Yeah, contact angle for those of you in Prager's lab. Talked about the log reduction value. Which makes you think, wow, those 99.9% are weak. And of course, don't forget, this is going to be a pore driven flow. So we're going to have to rely on that if you want to look at flux values. And And I think that was all we really talked about in terms of specifics to microfiltration. Maybe a little bit on modules. Single pass operation. We really didn't do a ton of this. This is going to be a lot of dead end filtration tests. All right, I think we called those the challenge tests to determine your LRB values. And knowing the difference between, what is it, screen filtration versus depth filtration.
Excuse me. Can I just, I want to just make sure, as I know, in equation 7.2 in the book, when delta V, it is 2 alpha cosine theta divided by diameters, am I right?
No,
There
it's
is
radius. That's a
radius?
misprint in the book.
Yeah, okay.
That equation solves for only the radius. To find the diameter, you have to double what it gives you.
Okay, so it is, because in the note, it's, I think it's written as diameters, I think.
I think it was, but I think I corrected it. If I haven't, let me know. But that, yeah, that was an
Can I check
unfortunate
that?
misprint.
Maybe, yeah, so it should be, okay. So in the book is wrong, so it should be, should be
Yeah.
diameter. Should be, R should be diameter.
Mm-hmm. If
Okay.
you wanted to make it diameter, it would be 4 gamma cosine over R or over
Okay,
D.
okay, I got it. Okay.
Any other questions? All right, the next section, at least according to the book, probably not how we did it, because this was the last thing I kind of clarified. We looked at gas separations, right? I like doing these problems, mass balance problems out of gas separations, because they're fun, at least for me. Definitely solution diffusion model. There's a lot here, right? We talked about selectivity. And this is also where pressure ratio and stage cut comes into play. And we had our special cases looking at pressure limited versus selectivity limited. Those approximations. The book goes into a whole lot of filler. This is what I tend to ignore in terms of the types of membranes, in terms of the chemistry. Feel free to read over that, but I didn't want this to be so much of a material science. I wanted to focus on, like, okay, I don't really care what the membrane's made out of. How do I use it? And so those are the big things I want you to get out of this. Also, the considerations when looking at multi-pass / multi-stage operations, right? How is that going to influence your expected membrane area, the power requirements, maybe the stage cut for each system, and then your overall selectivity. I don't want to say selectivity. We'll just leave it at that. Just so, be comfortable looking at, if I want you to compare a single stage versus a two-stage system, which one's going to have more membrane area, which one's going to probably have, more power requirements, which one's going to have a better overall separation and things like that. Was there anything in terms of the gas separation section that I can clarify?
Can you just clarify the third case, which is the between, in between?
The in
Because it's
between.
necessary, yeah, we should focus it or on just, because when I see that a long equation, and something like that, and I didn't get the idea, the concept, it is how to become between.
So the key thing to note is when you're looking at a pressure limited system, selectivity isn't really going to come into play because the driving forces aren't sufficiently high enough where that's going to be a major factor in your overall process. But as your driving force increases, then the membrane's ability to selectively separate things are going to be a factor. And so that's that kind of in between where both the pressure ratio in which the way the module's operating and the selectivity, which is being limited by the membrane, those are both going to be key factors. Then the flip side is when the pressure ratio is so high, you're not going to get a better separation out of the system because you're just going to be pushing more material in total through the membrane, but it's not going to be more selective through the membrane, if that makes sense. So you end up with the second case of being selectivity limited, which is why if you see in figure 812 and figure 813, that permeate concentration isn't changing. You might be getting more material through it, but the concentration is going to level off.
Okay.
Right, and so there's no gain by pushing more through.
Okay.
Yeah, and it is kind of an ugly equation, but the good news is with the using Excel, as long as you program it right, you gotta put it in once and you forget about it.
Oh, okay, got it.
If I made you do those kinds of things by hand, that would be a bigger issue. But if it was me on a final, I could see myself asking you guys, calculate selectivity and pressure ratio from this system, and I want you to tell me, is it going to be pressure limited? Is it going to be selectivity limited? And then based on that, tell me what the expected outlet concentration should be.
Mm-hmm.
Any other questions?
Excuse me, could you explain about, the gas mixture with component concentrations as a concentration? Because when I read, see the lectures and they read the book, something's, make something confuse me that they link, the concentration with the pressures, pressure. So in the book, so it's I don't get the ideas clearly.
Well, for a gas, concentration and partial pressures are going to be largely the same, right? If something's going to be 50% of your feed, the partial pressure in that system should be 50% that component if we're looking on a mole or volume basis.
Okay.
Now, if we're looking at extremely high pressures such that we can't rely on an ideal gas assumption, then we can say, okay, are we going to have to look at an equation of state? Because then things like fugacity is going to have to come into play, and non-ideal issues in terms of the thermodynamics become into play. But for pretty much this class, I don't consider the non-ideal coming into play because that's not the emphasis.
Oh, okay, got it.
If that makes sense.
Yeah,
because I don't like that's the multi-component class that we teach in undergrad. I want you guys to get the key concepts associated with how the membranes work and operate. And so for a gas, that's why we look at that. Concentration and partial pressure is going to be largely the same. Yeah, and I think some people have kind of gotten hung up on that. If I tell you something's 10% CO2, that's the concentration. It's 10% CO2. primarily because, you want to think of things in terms of, well, what is that in grams per liter? And I'm like, well, if I'm in a gas, I really don't care what it looks like grams per liter unless I want you to solve it on a mass basis. But for most gas systems, we can just calculate fluxes and things on a mole basis. It only gets really tricky if I give you something in weight percent. Then you can be like, well, do I convert? Do I need to convert? Or can I make it work?
Yeah.
Any other questions? All right, if there's no questions, I'll keep moving along. The next section we talked about, or I'm just going in the order of the book, was prevaporation. All right, so we're looking at our system. This is where it gets a little hairier because we got our liquid feed and our liquid retentate. And our vapor permeate. And so we kind of have two things happening here. We have vapor liquid equilibrium mixed with a membrane separation. Right, so we got, either we have a hot fluid, our feed is warm so we can get appreciable vapor pressure, or we have a vacuum driving force. And one of the things we looked at was our separation factor, or beta per vap, as a function of the selectivity separation factor of the membrane and separation factor via evaporation. And so that figure 9.6 is really key to kind of understand how each of those separation factors come into play. And we also looked at our special cases in this system, like in gas separations, where we have something that's either pressure limited or selectivity limited. Where for our pressure limited case, our beta membrane becomes a ratio of the partial pressures in the feed and the permeate. And for our selectivity limited, our beta membrane becomes our alpha membrane because we're limited by the selectivity of the membrane. Similar to when we don't have any pressure in the vacuum, in the permeate side, because we have a vacuum where that pressure is low. So is there any questions on prevaporation? It's another solution diffusion system. It's just a little different because we have that liquid feed. No? All right, the last thing was electrodialysis. This relies on ion exchange membranes, which are polymers with fixed charges on the backbones. In terms of transport, I think it confused more people than anything. The key thing to note is that the membranes selectively transport either cations or anions, but not both. We can determine, a limit to our driving force by our limiting current density. Heard about this, where our limiting current density is governed by this equation. But most of the time it's not calculated, it's measured experimentally, looking at a plot. I think it was a Cohen-Brown plot, looked like this, where the intersection between reciprocal current and resistance gave us our limiting current density. Where we had various data, something like that. Some other things to note is, looking at power consumption. It's I squared times R, and then our current efficiency. I'll clean that up. That really didn't help. Or eta C V dot delta C F over I. Which should be E over E theoretical. Or actually, sorry, E theoretical over E. As it's shown in the book. Any questions on electrodialysis? Can you guys there? Mohammed, if you're talking, I can't hear you.
Sorry?
Can you hear me? Hello, hello. You can?
Yes, I can hear you.
Okay. Any other questions?
Actually, yes, I do have a question.
Of course.
One of the things that confused me is on that graph of the inverse of current to resistance. What exactly is that the steep slope of the line? Is that's not like the resistance, is it?
How it kind of shoots up.
Right,
Yes.
right.
So what you're seeing is, okay, because since this is invert current, the bigger the value, the smaller the current applied, right?
Right.
And so what's happening is as you're increasing the current, you're increasing the voltage and operations following Ohm's law. But what happens is when secondary processes start coming into play, even as you start to increase the current, or the voltage is going to shoot up and your resistance is also going to shoot up because a bunch of other secondary processes are going to take over, primarily water splitting. And when you have water splitting in your system, you're going to have vapor. And the electrical resistance of water vapor within your cell is going to be orders of magnitude higher than the liquid within your system. And so that's a big part of why that resistance starts shooting way high. And so you look for the inflection, and that gives you kind of your barrier or your limiting current in terms of don't operate beyond here. Because essentially you lose Ohm's law due to all those secondary processes. You can also have electrode reactions. You can, depending on the system, especially if you got a lot of sodium chloride, you can make chlorine gas. A lot of not fun things can happen in these types of situations.
I guess, and that all makes sense, and I get that part. But I guess, I mean, just on a more like direct, the line all the way to the left, is that depicting like resistance?
Yes.
Okay. But
Yeah,
just
that
the setup of the graph, because I figured everything was on the x-axis. I figured it was two different currents that you were graphing against.
no,
one
you're
another.
you're graphing a bunch of different currents. Each point is a different current.
Right.
And so what it's saying is you really start getting to the point where you can't increase the current too much higher. Well, one, you're approaching, as you go below 1, that the currents all start to kind of collapse upon each other, but your resistance shoot up because everything else starts taking over. But yeah, that is the resistance.
Okay. And then I guess one more question I have about that is that I noticed that the line for the resistance is linear. Is that like how good of an approximation that things like still follow Ohm's law, like to a certain point? Like how good of an approximation is that?
It's really good.
Okay.
Typically to the point, if it's not, something's wrong.
Okay.
Because all those current efficiency and power consumption, everything we use to model is based off Ohm's law.
Okay.
And so when Ohm's law breaks down, we have an issue. The only cases where it doesn't is when we look at, say, other processes like electrodeionization, because we're kind of cheating Ohm's law a little bit to our benefit and some of those other processes. That with bipolar membrane, it's going to follow it a little bit, but you're going to see an increase in those power requirements, primarily because you want water splitting in that situation to get the acid and base formation.
Awesome. Thank you.
Of course. All right, guys, I think we're about out of time. Any last minute questions? I hope this was helpful. And I hope you've enjoyed this course. I really appreciate it, sincerely, you guys taking the course. I know this wasn't the best circumstance, but I hope you learn a little bit about membranes. I hope it wasn't too dry and dull, but I really do appreciate you guys sticking with me and working with me on this class.